No, it's okay. That's okay. Interesting. Of course not. I wouldn't expect you to, Karar. Okay. And do you have your maths book? No, of course not. Right. So standard error and confidence interval. And well, CI for confidence interval. So we'll start with confidence interval. For example, if we go back to heights, so a good trusty example of height, the average we said was like 160 or whatever, and the standard deviation is 10. Now there's some number so that if I mark, if I go to the left and the right by that number and draw the area in, this here will be 95%. That there's some number here and some number here that's the same distance from the centre, so that it covers 95% of the area. So what I'm looking for, yeah?
The next one is 170.
No, not necessarily. I'm looking for two numbers, 160 minus some number, height less than 160 plus the same number. I want this to be 95%. In other words, how far from the mean do I need to go left and right so that I cover 95% of the possible heights? So we can actually use our tables to find this out. But before we do that, we have to convert this into z's. Okay? So, KJ, you're not listening. So if I just go down for a little bit here, let's try and find the value in the table book. The number here, I'll call it minus z, and the number here, I'll call it z. And I want an area here of 95%. So think about how you might find that and try to find it for me.
You can check the 95% available and 95 on the table.
Nope. Not this.
To get the z.
Yes. So you are right, Fahad. You have to look up the table backwards. Roughly.
1%?
Backwards.
No.
How do you look backwards?
You find an answer of 0.95 and read off the z.
No, choose. We will look at the where it's 0. Because that's the only thing we've been doing.
Come here. Come here.
Me.
Come here, you. Yeah, you with the formula book.
1.6?
So look everywhere here. And we have used this, KJ, but I won't get angry right now because there's still lots of class time left to get angry. 0.95 is here, roughly. But it's not 0.95 we have to look up. I wonder what we're actually looking up.
The first.
For example, 955.
But it's not 0.95 or 955. Wait. Look up. Look up. Look up. Thank you. So, you want the area to the left of Z to be what? If you want this number here, to be what? About.
I see 1.7.
No. What area? What's the area to the left of Z?
95. No,
it's not, because 95 is only to here.
1.
No, it's not, because
1 minus z.
Z.
No, stop doing that thing where you're guessing answers and think, okay? If this is 95%, how much must be in the green part?
5.
5. So how much is in this green part?
2.5.
2.5. So how much is to the left of this number here? 97.5. So you need to actually look up 0.975 in the table.
975. Anywhere on the table.
1.9.
Yes, 1.9.
6.
Where's the 6 from?
Oh, KJ.
Okay, I understand now. You just
Oh, dang. Oh.
I was wondering what these were for.
Oh, look, Barry Allen's lost his powers. He can't read normal distribution tables anymore. Alright. Okay, so we got 1.96.
Yep.
Okay, now that's for the Z, not for the table we have here. Okay? So you remember our formula for the transformation called the Z transform? What was it? X minus mu over sigma. Now, in this case, we know the average, don't we?
Yeah.
What is it? 160. And the standard deviation? 10. And in this case, we know the Z, 1.96. Do we know the X? No, that's what we actually want. We want the X here. Yes. So, look, I want you to find this X here.
Could you go down?
Yeah. Do I here?
That's fine. 179. No, hold on. Yeah, 179.6.
What did you get?
179.6.
That's it, yeah. So if you have
What would
this,
be the unit?
huh?
What would be the unit?
Centimeters.
Sorry?
179.1.
6.
Yes.
Yeah? Yeah? Okay. No, I think it's just a cable actually. I'm not sure because, yeah, because this happened last time as well, and then when I got a new cable that fixed it. So I think the cable gets worn down from being plugged in and out so much. There we go. Okay. So you got 179.6. And here the average, the mean average is 160. Okay, what's this number here? KJ, this number here now. So if we go back to the Z graph, this is 1.96. So what's this here? Minus 1.96. So now we have minus 1.96 equals x minus 160 over 10. So give me the x for the left.
140.4.
140.4.
Yep.
So therefore, what's the probability that somebody will be between 140.4 and then 179.6? We picked those numbers to make it 95%. Are you writing this down? Yeah.
Could you zoom out and leave this, please? Yeah.
So this area in here, that's 95%. So this here, H from 140 centimeters to about 180 centimeters, this is called the 95% confidence interval.
Confidence what?
Interval.
Mm-hmm.
Meaning that 95% of people will be from 140 to 180 in height.
You approximated?
I just rounded off 140.4 and 179.6. Yeah?
I'm just finding the probability here.
Yeah, okay. This is called a confidence interval, and this is how you construct it. So we'll do another example. Again, we'll do something. Yeah? CI?
Yeah.
What's CI?
Oh,
It's, yeah. Got that? So let's look at an engineering one as an example. Okay, can I scroll down? Yeah. So, for example, again with the pen. New cable, yeah. But I keep thinking
which cable is it?
it's
Normal?
micro to normal.
The normal, the use.
The one that you use to charge up your phone.
Do you need one? I have one.
Well, let's see if it is the cable, because if it's not the cable, then I'll buy a new pad. The school will buy one for me. Oh, okay.
Are you going to buy wireless?
I was actually looking at that seriously, because then the cable won't get worn down. Let's see if it is the cable. No, I think it is the pad. Maybe it's the laptop.
Yeah, probably.
You know, 100 years.
Yeah, 100 years, yeah. From my grandfather. It passed down, yeah.
When you went to college, maybe.
That's it, yeah. That's
and
it.
you're still using it.
That's it. It has sentimental value.
You pass it down.
I'll leave it to one of my students.
Alright.
Why not? No, this might be the end.
Hopefully. Then you'll
No, it's still got some life. No, wait, hang on.
Then
It's still breathing, hang on. There's a pulse. Just need no, gently put the patient down. Okay. So, gently. That's terrible. We're back. Okay. So for this one here, we're manufacturing like nuts and bolts. So of course it has a diameter here. So we'll say that the diameter is normally distributed. It has a bell curve shape to how frequently the proportion of the height. So let's say this nut is on average 10 millimeters. And what do you feel like would be a suitable standard deviation for something like this?
1.
I think they'd be better than 1 millimeter. And I think the fluctuations will be definitely not 2. If you were making this much for an hour, you would be out of business quickly. Yeah.
In the mathematics, and then called nut.
No, just a nut and bolt, for like construction. Here, like,
Yeah,
like this.
It's not benzene.
It's not what? It's not what?
The benzene compound. Anyway.
No, it's not benzene. It's a nut. Yeah. Now, what will we say is the standard deviation? I would say 0.5 millimeter. So 0.5 millimeter is the standard deviation. So the average is 10 millimeters, and the standard deviation, I'd say, is 0.5 millimeter. Okay? What I want you to do for me, we'll construct the 90% confidence interval. So I want to know 90% of nuts will be between what size and what size. Do you understand?
Yeah.
Now 90%, not 95. So it's not 1.96. It'll be a smaller number this time.
1.3.
That's small? I don't think so.
Yeah, 1.3.
No, KJ, no.
What?
That is wrong.
You said?
That is wrong, KJ.
1.29?
That is even more wrong.
Exactly.
Hold on.
1.3.
No, no. That's what I said.
Oh. 1.2.
No. Guys, what number are you looking up? What number are you checking in your table book? Are you looking up 0.9?
No.
No, you better not be, because you just learned that's not the number to look up from the last example.
Yeah, exactly.
Yeah. So what number do you look up?
9.5.
No.
0.95.
Thank you, KJ. 0.95. And when you look this up, you got 1.65. This is the Z to use. Okay, construct a confidence interval, please. Okay, did you get them?
Yes.
Yeah, what's the upper one?
10.825.
Correct. And then the lower one?
9.175. Bam.
Okay. There is a slightly quicker way to do this calculation. When you want to make a confidence interval, okay, it's always going to be the average plus or not minus that Z value times the standard deviation. So in my last example, it was 10 millimeters plus or minus 1.65 times 0.5 millimeters. Yeah? What's wrong? Maybe. Are they just waiting outside? No. They won't be scared of KJ.
Exactly.
He's too friendly. Hey guys, do you mind moving?
Yeah.
Thank you.
Yeah, we do mind.
We're doing some serious maths
Do
in
mind
here.
moving? They said, yeah, they mind.
Yeah, what else? Alright. You see that there now? So this is a confidence interval. In fact, often there are three very common confidence intervals. So it actually is worth your while to, ignore them. It's worth your while to memorize these numbers to save time in the exam. So for a 90% confidence interval, what do we use for Z? Z equals 5. And for a 95% confidence interval, Z is 1.96. And for a 90, I think it's a 99% one, is 2. Let me just double check. 99, that would be 0.995. So yeah, 2 point, no, I don't want that one actually. I wanted 99. Hold on. I wanted 2. 97, okay. 1 sec. 1 minus 0.9. Yeah, okay. Yeah, 99%, sorry, 99% is 995. So that one is 2.57. So these three here, they're the most common confidence intervals. KJ, these three here are the most common confidence intervals you could be asked to construct in the exam. In fact, in particular, these two, and in particular, this one the most. So if you only remember one number to save time in the exam, remember 1.96. It's nearly 2. In fact, some people, it's quite common in a lot of courses to actually use 2, just to make the calculations a little quicker and easier to do if you're doing them in your head. So for example, let me show you what I mean by that. Imagine we are manufacturing cars, and I say that the average weight of the car we manufacture is 1,500 kilograms. Now, will each car be the same weight, the same mass? No, there'll be slight differences. How much of a standard deviation do you think there will be per each car? 100 grams? I don't think we're that precise. No. I think, there's going to be differences. Maybe a kilogram. The density in the metal might vary during the assembly line. So I'm going to say 1 kilogram is the standard deviation. So here's the trick that you can do in your head. What you can do mentally is you can add twice the standard deviation onto this, and what would you get? 1502, and then minus twice the standard deviation? 1498. So what you can say is, okay, I believe that 95% of the cars will be between these two masses. This is the purpose of confidence intervals. It puts boundaries on what you are thinking the value should be.
It's like a range of probability of that.
Yeah, but it's not even, you don't even have to say it's fancy as that. It's like if somebody said, I'm making a car and it should be 1,500 kilograms, you know that it won't be exactly 1,500. So the person says, okay, what do you think it will be? So you say, I think it will be between 1498 and 1502. And then they say, how confident are you it will be between these two numbers? We're 95% confident. Because we think 95% of the time it will be between these two.
Why did they choose 99 there? So it's closer.
Yeah. It's just a convention. So there's no rule. It's normally 95% is what's used. But this is why I showed you all three of them. So it depends on the manufacturing. So for example, in places like Japan, they would use more than 95% confidence interval. They would use 99% onwards. Okay? But if you're just manufacturing something that's not so important, then you could use 95% or 90%. Okay? So that's confidence interval. This is new to the syllabus, so it's likely to be on the exam. In fact, I think it's likely to be even a Section A question, so you can't avoid it. So you have to learn how to use this. But, like I said, they'll probably pick one of these three, so you could memorize the numbers if you don't know how to use this one. You get this one, yeah? And formula book. Yeah. Okay, next now, standard error. Okay. So let me actually open up the program. I'm going to give you some numbers, and I want you to get for me the standard error. Let me just check something. Actually, you know what? I want to open up if I have the formula book, but I don't think I have it. This table is in the formula book anyway, so don't you worry about that. No, the table you have, but I wanted to see. The only thing about the one that's in the formula book is I don't think they have a picture on the top. But I don't know if I have it. It's well, if you remember, it's the area to the left. You don't need it. Okay. And we are math engineering syllabus. You know what? I kind of want the formula book.
Have you updated the formula book on the
I don't know. I don't know. No.
Not now.
I will at some point. Don't worry. Do you know what? Actually, Fahad, I'll actually just open it up and just see what it looks like. Right. Okay, so this is the last section here. Okay, that's actually okay. Right. I can't get the formula book right this second. It doesn't matter. So, sorry, I was telling you I was opening up the program here. What I'm going to do next should remind you of something that you've seen in physics. So we'll imagine that there was some experiment done and we calculated some estimations for G, 9.81. Okay. Come on, you can do it. I don't need the Chrome anymore. Yeah, here we go. Right. So let's put in some values for G. So, for example, we have KJ's one, whatever, or Yemi's one, etc. Okay, 10. 9? 12. Yeah. Right, so these are our estimations for G. So if we had 1, 2, 3, what have we got? 7 estimations for G. What's the best one to use? No, we know what the answer is, of course, it's 9.81. But if we didn't know the answer, what would be the best one to use? No. The average. The average. So can you average these for me? Yeah, so if you get the average here, the mean, that would be, what did you get? 9.724. Remember in physics we said, okay, but we shouldn't say, our answer is no good unless we can put boundaries on it. Remember that? Yeah. So is it 9.7243? Well, we think it is, but there's some uncertainty. So for maths, what could we use as a measure of the uncertainty?
Units?
No, what mathematical calculation could we do to measure uncertainty? Standard deviation we could use. So standard deviation I'll write as S. You know how to calculate standard deviation, don't you? Standard, what's it? Standard dot, I'll have to look at the function of. No, it's different. It's different in this one. Standard deviation for that. Okay, so we calculate the standard deviation and we get 0.3. So what would you present as your answer in the report?
Plus or minus.
Plus or minus 0.3. In fact, when it comes to problems like this, the situation is actually better. Because, for example, let me just draw it here. Let's say you had, I did the experiment 100 times, and I got an average of 9.8 and a standard deviation of 0.1. That's pretty good, isn't it? Let's say someone else did it 10 times, their average was 9.8 and their standard deviation is 0.1. So in the first case and in the second case, you can make a confidence interval, but which situation is a more accurate, better situation? Whose result would you trust more? The first one, because there's a 100 data points, whereas the other one there's 10. So this is the small problem with standard deviation, that if you use standard deviation as a measure of uncertainty, it doesn't include the sample size for the experimental calculation. So there is something else that we can use which is like standard deviation. Standard error, hence the name of the lesson. Oops, no, cancel. So standard error is almost like standard deviation except for one difference. No, divide by the square root of the sample size. So how many have we got in our sample here? 7. Will this make it bigger or smaller? Smaller. And imagine we had 100 people, or points, and you see it's got much smaller. So instead of using standard deviation for these types of problems, we use standard error. So if I just go here, well no, I can leave it here. What is the mean here? 9.7. Standard error, 0.11. So in physics, what would we say is our estimation for the value here? We would say 9.7 plus or minus 0.11. But in maths, we could do something like use a 95% confidence interval. So it would be 9.7 plus or minus z times 0.11. So what do we use if we want 95% confidence for z? No. What was our z for 95%? 1.96. Yeah. In physics, what did we use for z? Well, we didn't use a z, did we? So the z was like... No. What number was z? It was like 1. Because we have the mean plus or minus 1 standard error. We didn't have a number in the standard error, did we? It was just
1 square root 1.
Yeah, it was just 1. Here. In physics, we said our answer would be this plus or minus this. So it's like we use z as 1. But of course I didn't tell you that because we haven't done it at the time. Look at your table book and you will find, I'll tell you now anyway, if you use z as 1, that's a 65% confidence interval, I believe. No, don't look at it just yet, just look at me. What?
84.
84? Is that good? That's better. No, it's not 84. 84 is to the left, remember? You have the tails. Hang on, I'll tell you what it is now. It is... Well, it's actually much better than I thought. 1. Pretty good, actually. It's like 92% or something. Or not 92. What's wrong here? It doesn't matter. It is. That doesn't matter. That's what I don't care about that right there. Anyway, in the exam, what you would get is something like some data. Can you imagine like it was a physics experiment and the question would be construct a 95% confidence interval. So what do you need to calculate first? The average. Then standard deviation. But we don't use the standard deviation. We use the standard error in these kind of physics problems. or not just physics, but any kind of experiment where you're repeating it n times to improve it. And then if it was 95%, what would I use for the z? For 95%? 1.96. So just to finish, can you actually calculate the confidence interval for the g here? So g would be less than, look, I'll just do it here. G would be less than this plus this times standard error. And g should be bigger than this minus z times standard error. Oops, I put it in the wrong spot. Hang on. Equals this minus this times this one. So what you're saying is, what do you think the value of g is? We think g is between 9.5 and 9.95. How confident are you about this? We are 95% confident about this prediction.
But you know, the standard error,
Yeah.
you divide by 100, right?
And this example, no, divide by,
Change it.
I changed it back, I think, square root 7. Square root now, square root. Yeah. And for example, if I was to change this to 100, will my interval get bigger or smaller?
Smaller.
Smaller. So if you did this experiment 100 times, you might get a result like this. Is this a better result to have? It is. It's closer to the true value. Yeah. This is standard error and confidence interval. I really think he will give you a confidence interval question this year because it's new to the course. Okay, so we've already done that. We'll talk more about that during revision. All right, goodbye.